Today we're going to begin our study of infinite series in AP Calculus BC. And I'm just going to begin with a basic function, y equals 2x. The full domain of that function is all real numbers. And we know the graph is a line, the slope at 2, it's a continuous function. Now a sequence is also a function, but it's a function in which the domain is the set of integers, and commonly it's the set of whole or natural numbers. So let me give you an example. So I'm going to write a sequence here. I'm going to say a sub n, or you've used t sub n in the past, term 1, term 2, term 3. I'm just going to call my sequence a sub n, and let's take 2n. And in this case, I'm going to let n be a natural number. N is 1, n is 2, n is 3. Now, by the way, there are lots of different ways to write sequences. A common way that you'll see is squiggly brackets with the formula inside, and on the outside the values of n that we're going to plug into that, from n equals 1 to n equals infinity, since we're going to be studying infinite series eventually. And so if we put different values of n in, if n is 1, the first term is 2. If we put n is 2 in, the next term is 4, n is 3, the next term is 6, and this goes on infinitely. So there's our sequence. And we can graph our sequence just like we can graph our function over the set of real numbers. Here we're going to plot the term number, and here the value of the term. And so term 1 is 2, term 2 is 4, term 3 is 6, etc. And the big difference you'll notice between the graph of these two is that the sequence graph is a set of points. It's discrete data, because we're only using as our domain, in this case, the set of natural numbers. Now your calculator will graph in sequence mode, so let's just look at that. So my calculator is set up with y equals 2x, press the graph, you get the continuous function. You know how to do that, but how do you graph it in sequence mode? So on your mode button right here, let's just move this over, press mode, and then down on the 5th line, I think that is, where it says function, move over to where it says SEQ, sequence, and then go back to y equals. Alright, so this is your y equals menu, and when you're entering your sequence, there's 3 things that you may need to plug in. At least 2 of them you'll need to plug in. First of all is the first value of n that you wanted to use. You want to use for your sequence. Well, since we were using natural numbers, our first natural number is n equals 1, so the n minimum is 1. The second line is your actual, the equation of your sequence. So u sub n, I was using a sub n, is 2n. And the X button here now will be an n, because we're in sequence mode. And now we want to graph this. And so if we go up to our window dimensions, let's graph the first 10 terms of this sequence. So from n equals 1 to n equals 10. Your plot start is fine at 1. Your x, which is your term numbers, well, that would match your n, min, and max from 1 to 10, but I'm just going to make this a little smaller so I can see a little bit further on either side. So let's go from -1 to 11. And the scale is 1 is good there. And the max, or the y values, are the output values. So this is going to be from 0. N equals 1 would be 2. So let's go a little bit lower than that. Let's go down to -2 just so we can see the axes. And the highest, if we're going to 10, 2 times 10 will be 20, so let's go to 22. And if you press graph, there you see the sequence graphed. If you trace it, term 1, term 2, term 3, a set of discrete points as we've discussed. Now I want to go back to our sequence for a moment and just represent it a little bit differently. At the moment, we have our sequence represented in terms of n. But sometimes it's also convenient to represent our sequence in terms of the previous term. So for example here, you'll notice that term 2, A2, can be found by taking term 1 and adding 2. Add 2. Add 2. Term 3 can be found by taking term 2 and adding 2. And this is what we call a recursive formula, because to determine a given term, a sub n, we're taking the previous term, a sub n plus minus 1, and adding 2. And this is great as long as we know the term that we're starting with. Well, the term that we're starting with, a1, we know is 2. And this is a recursive formula. And I mention that because you can write formulas recursively in your calculator as well. Alright, so we want to represent this recursive formula in our calculator. So back to sequence mode. And so what we're going to write is our first term is term 1, our n minimum is 1. Our formula is this. So u sub n will be u sub n minus 1. Alright, so u on the calculator is the little blue u right here on the 7. So second function u of n minus 1 plus 2. Now, with a recursive formula, you have to specify the first term. So that's what this third line is for. You would only use this third line when you're doing a recursive formula. Our first term we know is 2. And if we graph, we see that our sequence is represented the same as it was when we did the sequence just in terms of n. Let me show you one more way to represent a sequence on the calculator. This time I'm going to go to a blank screen. And this method will be useful when I don't need to have a graph of my sequence. I just want to have the terms listed. So I'm going to go to the list menu, which is above the stat. So second function stat, and over to ops, operations, and number 5, sequence. And I get asked a series of questions here. First of all, my expression, my formula is 2n. My variable is n. I've already got that in there. I'm still going to start with n equals 1, and let's go up to n equals 10. We'll look at the first 10 terms, and the step is 1. And if I press paste, what that will do is put it into a code the calculator can understand. Now, some of you that have the older calculators, you will have to enter your formula exactly like this. Formula with respect to n, starting, ending, and then the step, which is 1. And if I press enter, you'll notice that I get the terms 2, 4, 6, 8, etc. up to the end, to the 10th term, 2 times 10, which is 20. So lots of ways to represent sequences on the calculator. Alright, so I'm sure you find all that interesting in terms of how the calculator can do sequences, but where does this have to do with calculus? Well, what we're going to look at is limits of sequences going to infinity. And really that's the only limit we can investigate. Since our data points on sequences are discrete, you can't come from both sides of, for example, n equals 2, because they don't exist. N equals 1, n equals 2, n equals 3. So the only limit that makes sense to investigate is n going to infinity. Alright, a definition. A sequence, we say, converges to L if the limit of that sequence equals L. Okay, so if the sequence approaches a given number, we say it converges to L, and if it doesn't, then we say it diverges. So we're back to wanting to evaluate limits. Well, there's lots of good news to report here. First of all the limit properties that we studied of f of x also apply to sequences. So that's great news. And same thing with algebraic techniques. Any algebraic techniques that we use to evaluate this kind of limit also applies to this kind of limit. And of course f of x is related to a of n. It's the same equation, it's just that this is a continuous function and this is a discrete one. Okay, this is probably most of the real numbers with some restrictions perhaps. This is just a domain of integers, or more commonly whole numbers or natural numbers. So let's just take a look at an example or two with this. We have a limit of this sequence. We know it's a sequence because it's n. Is commonly used for sequences. Let's just look at this with the calculator for a few moments. And let's just review our calculator steps here. Let's suppose our sequence, operations 5. We have here our equation is n divided by e to the n. Variable n, and let's just look at the first 10 terms again. If I scroll down the list, what I'm looking for is the limit as n gets larger. Does this seem to be approaching a given value? Okay, well, it looks like it's going to 0. It's a little slow clicking here. Let's look at the function graphically. So we'll go up and we'll do a non-recursive formula, which means we don't need the third line here. We're going to go from term 1 and our formula n divided by e to the n. And let's look at our graph. Let's just make this -2 to 2. We trace. Certainly looks like the values of the sequence are going towards 0. Okay, so we have an intuitive feel for that. Now let's do it algebraically. So if we examine this, infinity on the top, e to the infinity would be infinity. I have an indeterminate form. And since we can use computational techniques we've studied for limits of functions, we can use that for sequences as well. So we're going to use L'Hopital's rule. We're going to do the derivative of the numerator and denominator, which would be 1 over e to the n. As n goes to infinity, e to the infinity goes to infinity, and 1 over infinity is 0. And so that confirms what I intuitively thought I would get by looking at it on the calculator. Alright, here's another limit of a sequence. Let's plug this one into the calculator just to get a sense of it. So our formula is -1 to the n. Now if you think about what that's going to do, if n is 1, that term will be -1. If n is 2, that term will be +1. If n is 3, that term will be -1. If n is 4, that term will be +1. So this -1 to the n is causing a positive-negative back and forth to happen. It's what we call alternating. And if I trace, do I seem to be closing in on something? I seem to be narrowing in on something. Looks like I'm narrowing in on 2. Okay, if I want to go further down the line, if I want to go to n equals 30, let's change our x max to 30. That's nice. You can definitely see it's approaching something. Looks like it's 2. Okay, let's try to evaluate the limit. Well, we know in our study of limits that if we're going to infinity, the 1's not going to matter much. 1 n here is going to cancel 1 n here. And we're going to have our alternating -1, +1, -1, +1 over something big. So that's going to go to 0, plus 2. That's going to make that go to 2. And so our limit converges, in this case, to 2.